Thank you everyone for joining in for our webinar today. Today we're going to be talking about forces. So if everyone wants to quickly refresh their mind on their first year physics of torque and very basic kinematics, that would be awesome. But I'm also going to do a very brief quick review without getting too much into the nitty-gritty. So list of forces. This presentation goes over when the force is unknown, then what do we do? Sometimes we're given designs or products where we're asked to fulfill a certain criteria, but we're not given the entire picture. We're not given everything, which is okay. Luckily, we don't always need that. So in our case, what is list of forces? Basically, we're going to be able to calculate forces on selected faces after we've run a study. And of course, our study depends, with our force equations, how well we place our fixtures, which I will cover briefly. And like I said earlier before, it doesn't require an initial force. So in our fixtures, say for example, we can have a reference geometry move something a certain distance, or we can have a displacement, right? And from that, we can calculate what the resultant forces will be, or just the internal forces, based on that displacement. And then furthermore, we can take that and say, okay, well, it also works for sheet metals, so there are also reaction forces that we can calculate, but it's not exclusive to sheet metals. And if we have our part interacting with something else, and we're only given, the displacement, it only takes this much distance to touch it, well, we can also calculate the forces that are going through that entire process. And as promised, very brief, quick physics review on torque. And this is with a mid-plane shell. You can see that black line in the middle of this, basically assuming a sheet metal part as just a flat piece. And to make the math easy, I said along this axis, we're just going to call that the resting position of theta, being 90 degrees. And so over that length of 150, since I already ran the study, I kind of cheated, and I know that we have 13.4 newtons, but it's just something to keep in mind because I want us to understand how the result, have that in mind so we can kind of trace all of every example that we go through, basically. So we have our force, 13.4 newtons over 150 millimeters, and that gives us 2 newton meters. And I will be bumping up to 20 millimeters eventually, and that'll basically just result in a higher force, but it's only a magnitude of 10 of difference. But something to keep in mind for when we get a little bit more into the different functionality and the different uses that we can use for result of forces. All right, without further ado, jump over into SOLIDWORKS. All right, and I'm going to start by going over our first ribbed solid. This is as per the first example of what we saw. So here I have our first fixture, and since it is a solid, we will not have our immovable option. It'll just lock down our translational motion here with our fixed geometry, which is what we want, right? If we're allowing this to rotate, then there's technically no torque. It's just giving out with whatever forces or displacement is pushing our part out from equilibrium, or where it's sitting in free space. And the fixed geometry allows us to actually get a good reading because it's sitting there. It's going to interact with whatever force is going on over here. And speaking of over here, we have our displacement. And I just said that this is going to be 2 millimeters right here. And it turns out if I move this up to 20 millimeters, we will get a small displacement, large displacement flag. And for the sake of example here, I'm not going to do that here. I will do that later, and I'll quickly talk about that. Though, since we're not going to be discussing nonlinear analysis, we're just kind of just talk about it, and I'm just going to state that once we get there. Sweet. So I have my study already run. Now, if we right-click our results folder, we can have this option list of result force. Very simply. And right now we have our reaction force uh, activated. If we have different criteria, we will see these options become available. Though since this is just a solid and it is just pretty basic example, we're not going to be given too many options. But a reaction force is pretty good for what we need. And like I said, since we lock down this face, we can anticipate that we're going to have the most amount of action or the most amount of um, energy exchange through this part right here. And if we click on it and click update, we are given with a resultant force or reaction force, excuse me, of 25.2 newtons. And that is with the rib. It is going to be different from what I once put up in the calculation because this is definitely giving a lot of more ability to resist that displacement because that is just, when you have rigid bodies, it's luckily going to help with resisting a lot of forces that are going on one side or the other. So that is great, and double check. We can also check our displacement. We can see here if we can get that to our Y displacement, just for reference. Great, and a great sanity check. We did displace it by 2 millimeters. So not much there. Next, I'm going to move over to when we have our no rib example. And for all you sheet metal guys out there, if you were looking at the icons here, yes, this is assumed to be a sheet metal. And if we wanted to treat this as a solid, luckily, we can just, boom, we can just throw that there. And now we don't have to run with the assumption of these two faces. And we can also trust, well, we're also choosing to trust the mesh refinement here. I'm going to quickly give that a quick run. Show you guys the mesh right there. So we can already see that, yeah, this is, for our first analysis, this is not a lot of elements through that. And we're just going to keep that in mind because, more mesh, more refined mesh, more high quality or finer mesh definitely get us better results because we're allowing a lot more elements. Of course, computational resources at the time. We have to take these things into consideration before we just converge on an answer and call it good. But without too much dilly-dally, just going to show the displacement again. Yes, it did displace, and we did not get a small or a large displacement flag, so we can say that this is reasonably trustworthy in a static study. And we're going to do another check of the reaction forces. And there we have 13.4 newtons with 2 millimeters. And again, this is a length of 150 millimeters and just 2 millimeters of displacement on that end. So that's really great, right? And this isn't just exclusive to this face. We can see what is going on here. And it makes sense because this would be stressed on this one side that it's being pushed on. So that is how we will read these points. I also have panelist Eric Vega joining us, and he will be kind of handling the Q&A. And of course, if you want to save your questions for after, that is totally all right as well. I'm going to have a kind of a quick one, so we'll have some time for discussion afterwards. Great. Now, since we quickly went over the mesh, now I'm going to talk about when we would want to make that a shell, because seeing this mesh, this is kind of an example of when we would have enough elements to where we can argue, oh, okay, we can keep it a solid. But if we have that mesh like I showed you guys just before, our element density is not, where is it? Show my mesh. We don't have 3 elements across this length, So it would actually make sense to just assume this as a shell, uh, because we want, it'll luckily, will be fine with this just being assumed to be a thin plate. And I'll show that to you now. Cool. Luckily, let's see, let's treat this as a sheet metal, and you can always just go to your part, and I have already kind of, since this is a sheet metal part, we're going to have a cut list. I'm going to go down to sheet metal, and just to show it off, I'm going to edit the definition. Basically just choose our two sides to say, okay, from this side to this side, we're going to say we want this to be a thin of, I think it looks like I specified 2.5 millimeters. And it'll also ask you to, if you want it mid-plane or bottom. We've always run with bottom. It's basically saying below the surface, that's where we want our part to exist. However, when it starts the results, it'll take it to a 2D format, but our results will still work the same. And just to check, cool. I'm going to change this to 2 millimeters for congruency, and then we'll bump it up to 20 millimeters so I can show you the large displacement flag. So we got our 2 millimeters displacement. Run this really quickly. Nice. All right, so we got our stress, got our displacement. We'll check our list result force. Click this side because this is where we were getting our torque measurements, and look at that, 2.2 Newton meters. So luckily, it's working really great, and we did it as a sheet metal part. And we can even also go this for free body force. Check our stresses, our resultant torque. All right. Now we are going to go quickly back, jump back to talk about contact forces. Contact forces are when we'll be having surface-to-surface contact, sometimes node-to-surface contact, and we'll need to know how to interpret that, right? So certain faces, basically we'll just open a split line for that and just show off one surface to a surface. And the node to surface will show the criteria for that. Because sometimes our solids will need a little bit better definition. We'll activate this guy. And it is in a solid. We have high quality mesh, fixed geometry for both of these guys. Quickly show you this guy again. And since they are solids, they are in fixed geometry. And we have our displacement. I also want to mention that this is on this face. Even though it's a solid, we could have chosen this side to put our displacement on, right? So say this side had the acting displacement being pushed on it. Now we're going to have this side being pushed on, which will effectively still give us a similar result because we're still checking on the interaction between the edge of our plates to the face of our block. But reminder, this face of the block can be really anything. You know, it can be a cylinder, it can be a beam, you know, whatever it is, you can always just represent that with very basic geometry and take the readings that way. And the contact set that I chose for this, just a no penetration contact from face to face. So we have the first face. See if I can get a good show of that just on the inside of this plate. And the second face contact is this block. And chose surface to surface. If we have a sheet metal, which is just a flat piece, then we could probably to node to surface, but for this example, I just chose surface to surface because it made sense, because it's a solid object, right? Right. And these are the same. And we have 2 millimeters here. For this, we're going to check out our result forces. And let's just check this again. See how things are going. Remember that rib's going to have a lot more internal resistance to moving, so it's going to be required to, there's going to be a lot more torque to move this 2 millimeters, so that is going to be how much we are getting, 78.1 newtons as per its geometry. Let's open up these stress plots and see what we got. So it looks like, obviously makes contact with this face at just 2 millimeters. And if we wanted to check, let's see what's going on with the face of the part. Contact friction force. You notice our reaction force is not going to be, it's not going to really work, but now our contact force. Reading quite a lot of newtons, shall we say. And we can also do this for the face that will be interacting with our parts. Maybe not. No worries. Sweet. Now this guy, fortunately, just had to activate this, and we will unsuppress our block. All right. So now that we have covered what goes on, actually, I want to run this on the face. Like I was saying, for more refined meshes, this will take more time because we are definitely boosting our number of nodes and elements. And another thing we should note is, if you guys noticed, we do have a force this time. Now we say we have the force finally, or we just want to see what's going to happen to this part, we can still use the result force this way. And the reason we want to do this is because we want to understand how things can be displaced, the relationship between displacement, between forces. If we are given the force, but we don't know the displacement, we can still find that out, and there's an easy out for that, definitely. And the result force will give us a little bit better of a definition of how the forces are interacting within a given force, because we'll still have stresses that are put throughout the faces of the sheet, the metal plate. The block will also have some things that are going on there. Gosh, I apologize. There we go. All right. Let's check out what we got here. So with 25 newtons being pushed on that face, let's kind of probe around and see what we got here. We got our contact friction force on our face. Check that out. Definitely a little bit less than what we had before. It's also interesting to see how when we are seeing the pushback on this, how much force equal and opposite is actually undergoing in just that one simple kind of displacement. And of course, we need to check the displacement. You can come in over here and say, hey, that's nice you're giving us a resultant displacement, but we're looking for the Y displacement, just something a little more specific. Sweet. And we have that 2 millimeters. And as I said before, I'm just going to quickly go over why I chose 2 millimeters. It's something that you may run into when you're working with static study and forces. You may get what is called a large displacement flag. And what is a large displacement flag? Basically, it's saying your part is moving 10% out of its kind of resting position. Wherever it is sitting, wherever it's fixtured, its displacement is being disfigured. And past that point, static analysis is only going to consider forces coming in or a displacement from this one position even after it bends out of place. So we'll run this one. I promise it is exorbitantly faster. Boom, and check that out. So excessive displacements were calculated in this model. If your system is properly restrained, consider using large displacement option to improve the accuracy of calculations. We recommend to not click no to solve with small displacement. Since it is just a static study, we're not going to have the most trustworthy results if we continue to run this after it's already been displaced, because this is essentially where all of our forces and displacement is going to be referenced. And it's just going to continue pushing from that point, versus if we had a linear static study, it'll take this and go, oh, okay, you want to continue at this point here, not from all the way at our resting position. So that is something that is something you want to keep in mind, that when we still have just a small displacement, or we say, we want to just keep the small displacement, right, and don't work with the large displacement, we're still going to get something that is relatively very, very represented to be accurate, but any point after this is going to be inaccurate. And reminder, I did set this to 20 millimeters of displacement, so if you remember, we were getting 2 Newton meters, now we're just getting 20 Newton meters because I just bumped up the scale by 10. All right, and that actually is just the quick and dirty. And that's actually our conclusion for list of result forces. I do have a couple minutes left, so if you guys want to unmute yourself and ask a few questions or keep throwing them in chat, feel free to keep them coming. Looks like we have a question about the calculated angles. Yeah. So I'll just at least show what in the calculations. Though we have, let's say, for this example, we had 20 Newton meters. You can always throw that in an arcsine equation to find the resultant angle. That'll also give you that too. Or if you throw that angle in your sine function, that should give you a number you can also plug in to let me bring back that force equation, because everyone loves some math, right? Sorry about that. Right, so we have our theta. And reminder, I had that theta just at 90 degrees because I decided this would be my y origin because it's at resting position. Though if you already have it bumped out of place, you can just arc sign that that displacement to find your right angle, or correct angle, I should say. Just gonna pop open the chat. Great. And reminder, we do have a YouTube channel. We also have our website, goengineer.com, where you can also schedule AMS meetings for us. And we have Eric throwing that into the chat. Thank you very much. Always appreciated. Sweet. Yeah, and a reminder, if you guys do have further questions or want one-on-one time with me or Eric, you can always schedule us on goengineer.com under the support tab for application mentoring sessions. And there's still a lot more detail that we can get into as well. So, and we can also kind of help diagnose and understand how we can apply these methods to you guys' examples. But thank you for joining us. It's been a quick one for this time, but I hope everyone has a great rest of their day.